Welcome to our lecture about binary relations. We're in section 8.1 of F's book, Discrete Mathematics with Applications. So today we're going to talk about binary relations from one set A to another set B, or from a set A to itself. Let's pin this page of notes, and we can make these smaller. And here we go. Binary relations, plural. So here's our definition. Given sets A and B, a binary relation from A to B, that's what we're defining, a binary relation from A to B, it's really simple, any subset of A cross B. So just to make sure everybody remembers what A cross B means, recall, A cross B is a set. What do the elements look like? Ordered pairs, little a comma little b, where little a comes from set big A and little b comes from set big B. We call little a the first coordinate, little b the second coordinate, right? And the size of A cross B is the product of the sizes of A and B. So let's get right to an example. Given A equals the set containing, say, 2, 3, and 4, and B being the set containing 2, 4, 6, and 8, consider these binary relations from A to B. 1, we'll call it curly R1. We often use curly letters, capital letters, for binary relations or relations in general. Curly for relation R, and it's a capital letter because these are sets. These are subsets. It's any subset of A cross B, okay? So ordered pairs from A cross B. I'm not going to write all of A cross B, but you could do as a way of practicing. How big is A cross B itself? 3 choices for the first coordinate, because there are 3 elements in A, times 4 choices for the second coordinate. 3 times 4, or 12 ordered pairs, would be in A cross B. Let's pick some of those. For example, 2, 4. The 2 coming from A, the 4 coming from B. That's an element of A cross B, so it can be an element of any binary relation from A to B. Or we could say 3, 4, 3, 6, and 4, 8. This is just a random selection of 4 elements from A cross B. Remember, A cross B has 12 elements. We're building a subset. We could actually build all of A cross B and call it a binary relation from A to B, because any set is a subset of itself. So A cross B is a subset of A cross B, of course. That would be the largest binary relation from A to B, the whole of A cross B. What would the smallest binary relation from A to B be? B. That's right, the empty set. The empty set has no elements, but it is a subset of every set, including the set A cross B. So the smallest binary relation is always the empty set for any A and B. The largest binary relation from A to B is all of A cross B. And then there are a slew, usually, of binary relations that are in between 0 in size and the size of A times the size of B in size. Here I picked 4. Now, 2, let's call this relation R2. 3, 2, 3, 4, 3, 6, 4, 4, 4, 6, and 4, 8. Here I picked 1, 2, 3, 4, 5, 6 of the elements from A cross B to build a binary relation. There's nothing special about these 2 examples. I've just picked some elements from A cross B to show you that any subset of A cross B is technically a binary relation from A to B. Notation. example 1, let's look at R1. Notice in R1, we have the ordered pair 2, 4. Well, we could write that as follows. We could say 2 is R1 to 4. 3 is also R1 to 4, or we might just say 3 is related to 4. If there aren't any other relations in the problem, we'll just say related to. But if there's several relations and we're playing games with different relations, we'll name them and make sure we're discussing the appropriate relation. 3 is R1 to 6, and 4 is R1 to 8. Now, order matters. Order really does matter in these binary relations. Hang on, what's going on with this? Here we go. Order matters because these are ordered pairs. So whereas in relation 1, 2 is related to 4, 4 is not related to 2. For 4 to be related to 2, we would need to have the ordered pair 4, 2 in R1. So now let's look at R2. There are 6 statements of this form that we could write concerning R2. So you write the 6, I'll say small statements using this new notation about the relation R2 using the X, R, Y notation. This becomes a really handy notation, especially when we start to talk about properties of relations. Now, this is a very simple example. Generally, examples about some element of A being related to some element of B is based on a rule. Binary relations do reflect reality. Let's take a look at another example. Example 3. Here, I'd like to say we're going to let C be the elements 1, 2, and 3. By the way, this is another example with numerical elements, but the elements of these sets don't have to be numbers. We could play games with the elements being other sets, for example, or we could be playing games with sets of strings written over, say, the alphabet 0, 1, in other words, binary strings. Here we're just keeping with numerical examples. Let's say D is the set 2, 4, and 6. We're going to define a binary relation from C to D by this rule. So I want to show you that sometimes the way that a relation is presented is not as a set of ordered pairs just listed for you, but as a rule where we use the rule to figure out what the ordered pairs in the relation actually are. So think about this rule. C is going to be related, we'll call it R3, related to D, if and only if C divides D. Now this is a binary relation from set C to set D. Element little c is understood to come from set C, of course. Element little d comes from set D, big D. And the relation is, hey, we're going to make an ordered pair, little c, comma, little d, and put that in this relation, R3, if and only if D is equal to C times M for some M that, of course, is an integer, right? That's the definition of divides. So let's find this relation, curly R3. Let's find the elements ourselves using the rule. Okay. So example 3 continued. Here's our work. Find C, excuse me, not C, we know what C is. Find R3. Let's find that binary relation. We're going to write it as a set. Okay. So R3, here's our solution. R3 is a set. So we always put these elements into set brackets because these are subsets. This is a subset of C cross D, defined by this rule. So let's take a look. We want to pick a first coordinate and a second coordinate in such a way that the first coordinate divides into the second coordinate. So let's start with the first coordinate 1 from set C. Are there any elements of set D where we can say 1 divides the element from D? Sure. 1 divides into every integer. So 1 comma 2 is in R3. 1 divides 4. So we'll put 1, 4 in R3. And 1 divides into 6. So those are 3 of the elements in R3. What else is in R3? Well, let's see. We've exhausted all of the possible elements that have 1 as a first coordinate because 1 divided everything in D. So all 3 of those are there, 1 for each element of D using the element 1 from C. Let's look at the element 2 from C. Does 2 divide little d for any of the elements D, little d here in set D? Sure. 2 divides into 2. So 2, 2 is in R3. 2 also divides 4. And 2 divides 6. Now let's see if we can make any ordered pairs with 3 as the first coordinate. 3 does not divide 2. 3 does not divide 4. 3 does divide 6. In fact, I think we have room right here to put that last element of R3. Not too tight, just fits with room to close the set brackets. So this is the relation, curly R3, where we used a rule to define the relation. Let's do another one of these. Let's let capital M be the set 3, 4, 5, and 6. And let's let capital N be the set that contains 2, 4, 6, 8, and 10. We're going to define, and I'll write it a little differently this time, relation R4, subset of M cross N. So this is another way of saying that this relation R4 is a relation from M to N. Remember, any subset of M cross N is technically a binary relation from M to N. So we're going to define curly R4, a binary relation from M to N, subset of M cross N by the rule. Little m is R4 to little n if and only if M and N share at least one common prime factor. Okay, and this is for all elements little m and m, and for all elements little n and n, of course. This is sort of redundant, but I'll just write it there. So this is a rule to define R4, and we'd like to, of course, find R4. So when we are asked to find a relation, we're finding a set. We're finding a subset of M cross N where the ordered pairs will satisfy the rule that M and N share at least one common prime factor. Okay? So, I mean, there are numerous ways to write this. So each problem, I'm trying to write the instructions in a slightly different way so that you can start to kind of make those connections. So R4, we want to put elements in R4 where the coordinates of an ordered pair share a common prime factor, at least one common prime factor. All right, here we go. Let's look at the element 3 in set M. Now it's prime. Its only prime factor is 3. It can only be related to numbers in N that also have 3 as a prime factor, because it's the only possibility of a common prime factor with 3. 3 only has 3 as its prime factor. Well, so 3 is not going to be related to 2 because 2 doesn't have 3 as a prime factor. 3 is not going to be related to 4 either. But 3 is related to 6 because 3 and 6 share a common prime factor, namely 3. So let's put our first ordered pair into R4, 3, 6. All right, let's see if 3 is going to be related to 8. Nope. The standard factored form of 8 is 8 equals 2 cubed, so it's just got the prime factor 2 in it. No 3's there. Let's check 3 and 10. Do they share a common prime factor? Nope. So we've exhausted the possibility of using 3 as a first coordinate. There's only one ordered pair with 3 as the first coordinate, namely 3, 6. Let's move on to 4. Now 4 is 2 times 2, so its only prime factor is 2. It'll be related to any of the elements in N that have 2 as one of the prime factors. And of course, all of these elements are even. So 4 is actually going to be related to all of the elements in N. So 4, 2 share a common prime factor, namely 2. 4 and 4 share a common prime factor, again, 2. 4 and 6 share 2 as a prime factor. 4 and 8 share 2 as a prime factor. 4 and 10 share 2 as a prime factor. Okay, so 4 is related to everything over in N. Now let's look at 5. 5 only has 5 as its prime factor. It's not going to be related to 2, 4, 6, or 8 because none of those have prime 5 as a factor, but 10 does have 5 as a prime factor, so we're going to put 5, 10 into R4. Everybody with me? Let's look at 6. It has factors 2 and 3. Well, so 6 will be related to 2. 6 will be related to 4 because they both have 2 as a common prime factor. 6 will be related to 6 for 2 different reasons. 6 shares the prime factor 2 with itself, and it also shares the prime factor 3 with itself. In any case, that's enough to get 6, 6, 6 in there. What about 6 and 8? Is 6 R4 to 8? Is 6 related to 8? Sure. They both share the common prime factor 2, and 6 and 10 share 2 as a common prime factor. So that's R4. Elements are in R4. Ordered pairs are in R4 if and only if the 2 coordinates share at least one prime factor. So that's another way to see a rule defining a binary relation from a set to a set. I'd like you to be sure and read example 8.1.1 in the ebook. It's an example of an infinite binary relation from the reals to the reals. So I'd like you to read that so that you can see first an example of an infinite binary relation and also a binary relation on a non-finite set, namely the reals. Now let's look at another example here, example 5. And we are going to look at an infinite relation. So we're not going to be able to list the elements, but it's a very, very famous relation called congruence mod 2. Now remember the mod and the div functions based on the quotient remainder theorem using, well now, 2 as the divisor. D is 2. We're dividing integers by 2. Congruence mod 2 is a binary relation from Z to Z. So congruence mod 2 is a binary relation from Z to Z defined as follows. For all A and B and Z, let's see what the notation is that she's using. A is E to B if and only if. So we're using capital E. You know, I'm going to make that a curly E because the way I was taught, binary relations are always denoted by uppercase, curly or cursive letters, unless we use some completely different kind of symbol. And there is one for congruence mod 2. So we're going to use curly E. A is going to be curly E to B if and only if 2 divides the difference A minus B. Remember dividing by 2? The QR theorem says, hey, if you divide an integer by 2, you're going to get one of 2 different remainders. You're either going to get a remainder of 0, that means the integer you're dividing by 2 is even, of course, or you're going to get a remainder of +1, which means that the integer is odd. So if we just remember what we did a while back with the number line, we played sort of a bees on a chain game where if the remainder was 0, we'll just put a circle to indicate the integers that would yield a remainder of 0 when divided by 2. And it's every other integer, of course. It's all the evens. And then we can make a green square for the remainder being 1. We're dividing by 2. Dividing by 2. So the odds all yield that remainder of 1, right? So these alternate. And if we think about what this binary relation, congruence mod 2, is doing, it's saying if the distance between A and B is divisible by 2, then A and B are related. Okay. We're calling this congruence mod 2 relation curly E. Congruence mod 2. So let's just think about it. The evens are always a multiple of 2 apart from each other, right? -4 and -2 are 2 apart. That's a multiple of 2. -4 and 0 are 4 apart. That's divisible by 2. 4 and -4 are 8 apart. That's a multiple of 2. 2 divides that. So all the evens are related to one another by this congruence mod 2 relation. Same way with the odds. The odds are all related to one another because the difference between any 2 odd numbers is a multiple of 2. 2 divides the difference between, say, -1 and 3. They're 4 apart. 2 divides 4. -1 and 5 are 6 apart, right? 6 is a multiple of 2. So what this congruence mod 2 relation does is it separates the integers into 2 groups, the evens and the odds. So example 5 part A, let's just practice this idea. Find 4 ordered pairs involving three as one of the coordinates. I should say 4 ordered pairs in this relation curly E, of course. What else would I be talking about? But let's make that clear. All right. So we want to find 4 ordered pairs that have 3 as one of the coordinates. And these have to be in E. So, well, let's just think about it. 3, comma 3, I claim, is in E because 3 minus 3 is 0. And 0 is divisible by 2. It's 2 times 0, of course. So 3 is actually related to itself. It's 0 distance from itself, right? And 0 is a multiple of 2. 3 comma 6 is in this relation congruence mod 2, which we're calling curly E. Why? Well, because 3 minus 6, did I say 3 comma 6? And 3 isn't related to 6. Why? The difference between 3 and 6, right? 3 minus 6 is negative 3. That's not even. 2 doesn't divide that. Let's change this. How about 3 and 7? Better. Because the distance between 3 and 7, or 3 minus 7, is negative 4, and that's 2 times negative 2. All the odds have to go with odds. Let's put 3 as a second coordinate, and let's find a first coordinate. How about negative 9? Negative 9 minus 3, right? We're looking at the relation. We're looking at A minus B, and we're seeing if it's divisible by 2, is negative 12, and that's divisible by 2 because negative 12 is 2 times negative 6. How about negative 17 and 3? That's in E because negative 17 minus 3 is negative 20. And that's certainly a multiple of 2. Now, I don't want you to think that the first coordinates are going to have to be negative if the second coordinate is 3. So just to do a little bit more here than I said we needed to do, why don't we put 19 and 3? That's in E. Why? Because 19 minus 3 is 16, and that's, of course, 2 times 8. So, in fact, any integer of the form 2k plus 1 will be related to any integer of the form 2j plus 1 because the odds are always a distance apart that's a multiple of 2. This is for any k and j in Z. So any odd will be related to any odd. Now, the same goes with the evens. Find several ordered pairs in E that have 4 as one of the coordinates. Now, we already saw 4 here. It's an even number, and it's going to be related to any of the other even numbers that we see here or that don't appear there because they're too far down the number line. But, you know, you can certainly pick as many or as few as you feel like. I'll just do a few here because I think we're getting the drift. I just want to keep this definition where we can see it. So we want 4 to be one of the coordinates. Well, how about the ordered pair 4, 0? That's in E, because 4 minus 0 is 4, and of course that's a multiple of 2. It's 2 times 2. 4 is going to be related to itself for the same reason that 3 was related to itself, because 4 minus 4 is 0, and 0 is a multiple of 2. It's the 0th multiple. Let's try with a negative number like negative 12 and 4. That's in curly E. Well, that's a sign. Oh, not quite. Curly E, right? Because negative 12 minus 4 is negative 16. And of course, that's 2 times negative 8. And you're getting the drift, right? We could put 104. That's in E, because 100 minus 4 is 96. And that's 2 times, well, see, if it was 100, it'd be 2 times 50. If it was 98, it'd be 2 times 49. It's 96, it's 2 times 48. Okay, and so in fact, 2K, comma 2J is always going to be in E for any K and J in Z. In other words, any even number is going to be related to any other even number, right? So I'll just leave you with a do later. And I'm just going to put the definition up here that A, B is in E if and only if this 2 divides A minus B. So I'll leave you a do later. True or false? Zero is E to 0. True or false? Negative 3 is E to 5. 14 is E to negative 7. And 25 is E to 5. So you can just, it's basically saying, is the order pair 0, 0 in E? Is the order pair negative 3, 5 in E? Is the order pair 14, negative 7 in E? Is the order pair 25, 5 in E? So we'll come back to this and do some more shortly, but this is part 1 of our lecture for section 8.1. See you soon.